So what I'm going to be talking about today is some sort of introduction to a large and very influential area that arose from our field but has applications in many areas. And despite really a lot of investigations and research over 4 decades already, as you will see, it's quite amazing the questions that remain open. And these are not questions that people did not look at. These are very fundamental questions are open, and there is a lot to do. So I'm going to present some open questions. And then my goal is to show you a proof of a wonderful result of Matuszak from 1996, but that a little modification of it that gives something stronger. And it uses tools that maybe were not really typically used in this field, a little bit of algebraic geometry, even though it's a question about Banach spaces and embeddings. So the main theorem that I'm going to show is not mine, but it is some new perspective on an old result. But we'll get to that. But so really a tiny bit of terminology. So say a Banach space X admits a metric dimension reduction if, and this is going to be an obvious definition except for some choice of asymptotics that I will explain. If so, there exists some number alpha, a distortion, depends on the space, okay, such that for every n and for every n points in the space, there you can find a finite dimensional linear subspace F such that as maybe end points lying in this low dimensional subspace such that, so the first thing is the by-Lipschitz condition, so xi minus xj is less than yi minus yj, and less than this alpha, which was a parameter of the setting, xi minus xj for every I and j. This is not interesting at all, just take f to be their span. But 2, we want the dimension of the subspace to be n to the little of 1. So smaller than any power of n. I'll say a word about this n to the little of 1 in a second. And of course, this also depends on the space. So it's a property of the space. Okay? So the constant there is allowed to depend on the space. And then for the, so maybe that's another terminology is that X admits average metric dimension reduction if in the same quantifiers, but the conclusion is that we want this to hold an average. So we ask for much less. So it's the same quantifiers. I'm not copying them, and we still want the Lipschitz condition. We'll see later that we can do with less, but for now, for simplicity, this is for every ij. But for the injectivity, I just want the average distance to be preserved. So 1 over n squared yi minus yj the average distance that you see in the image is at least. Well, we can make them equal by normalization. And the same too, so the same thing. Okay, so this is just saying we want to embed with distortion alpha, but alpha is a constant depending only on the space, but not the endpoints, into some low-dimensional subspace. And here we're asking for much less. We don't really care about preserving all pairwise distances. We just want the average to be fine. Okay, so an impossibility result will be means here, for example, finding a configuration of points inside X, which is really intrinsically high-dimensional in the sense that you cannot realize it in any low-dimensional subspace, even if you only care about the average distance. Okay? And we'll get to that. So why n to the little of 1? So really, when I'll write down what's known, little o of n is interesting in any case, in all the cases that are not known. N is trivial, just put the points in their span, so go to little o of that. N to the little of 1 is a benchmark in the sense that all the known impossibility results break exactly there. That's why I chose this terminology. And there are also technical reasons, which I will not get into, that this is the dimension which makes certain applications become non-trivial. So there are all kinds of applications in which the end result depends on the log of the dimension. So the log of the dimension becomes the little o of log n precisely in this range. And in all of those cases, log n is somehow an easy theorem, which follows from Bourgain's embedding theorem, etc. So there is a technical reason why n to the little of 1 is interesting, but this is really just seems to be the benchmark. Nevertheless, in all the unknown examples, and there are many of them, if you get a little o of 1, that would be great. Okay, so don't focus too much on the asymptotics, but just on the big picture that we want to lower the dimension. Okay, so is the terminology clear? So what are the spaces for which we know that there is dimension reduction? So spaces that admit metric dimension reduction, or well, known, that are known to metric dimension reduction. So despite truly a lot of work and many papers which have dimension reduction in their title, we only know of 2 spaces. One of them is Hilbert space. This is Johnson-Lindenstrauss. '83. Okay, and here you just take your endpoints, think of them as lying in our N, and project them randomly onto a log n dimensional subspace. So the N to the little of 1 can actually be log n. And so this is something that is extremely influential and used a lot. But really the optimal dimension, the optimal proof was already given in the initial paper. So this you can prove that random projection is the best distribution over random matrices for this lemma, etc. So Hilbert space is great. So I would just say, so dim F here is actually big O of log n. Okay. And then there is the T2, so the 2 convexification of the Tierson space. This also gets dim F to be a big O of log n. And this was noted in a paper of Johnson and myself from something like 2010, maybe, I'm not so sure. So this is a space which isn't barely non-isomorphic to a Hilbert space, and still every endpoints can be realized in a logarithmically dimensional, log n dimensional subspace. And when the meat behind this dimension reduction result is structural properties of the space, but again, the Johnson-Indishaus lemma. So these endpoints, you look at their span, you can decompose the span as a direct sum, as some perhaps complicated log n dimensional subspace and the Hilbert space. And in the piece which is a Hilbert space, you do a random projection. So even though this is a new space, and this is not just the Johnson-Indishaus lemma, that's behind the scenes, it's still random projections. And that's the limit of what we know. Okay, so so that's all. These are the only two spaces for which we know that there is metric dimension reduction. Space is not admitting, so that's maybe. So spaces not admitting without metric dimension reduction, again, known to, so the first example that was proved was Hennenfent, and this is the result I'm going to discuss. It's a landmark contribution of Matuszak from '96. I'm going to discuss its proof. So I write it infinity, but in this formulation, what does this mean? Every metric space is isometric to a subset of L infinity, and every finite dimensional norm space is a candidate for F. So this is really a much more fundamental and general theorem than just saying L infinity. It says what is the question of dimension reduction in L infinity is the same as saying give me an arbitrary metric space and points and embed it into some low dimensional norm space. Okay, so this is, I wrote L infinity, but that's really a code for the general theorem. So this answered that there was a long line of investigation. This was asked in the initial Johnson-Indishaus paper, asked. And they conjectured that actually you can do so they conjectured. So the formulation is every endpoint metric space embedded into some normed space of dimension log n. There is a reason for this, what's motivation for this. In '85, Bourgain proved that the answer is no. So Bourgain proved, so this is 1985, that sometimes you need, so sometimes for some spaces, for some random construction, we need the dimension to be worse than log n, but barely. I mean, it's still a power of log, so at least some constant, some log n over log n squared. So it's a little bit worse, but there was, he asked whether you can do a power of log n in general, there is some history which I will not get into just to save time. Prior to Matuszak's '96 proof, there was an important paper of Linia, London, and Rabinovich, which I will get to a bit later, where they removed the log-log. So that's a very partial characterization of what they did. They actually came up with an important class of examples that was useful, but they removed the log-log. But then, as I said, Matuszak proved that L infinity does not satisfy metric dimension reduction, which in our formulation means that there exists endpoint metric spaces that require, if you want to embed them into any normed space of dimension k, k has to be some fixed power of n. So exponentially worse than the initial conjecture. That's what the Matuszak theorem says, and we'll formulate exactly, and we'll prove it later. Okay, so that was the first big result, and then, so L1 is known not to. This is, again, a famous theorem of Brinkman and Charikar. in 2003. And many people thought about this before, and this is was a very high-profile result at the time. So in L1, you can find a collection of endpoints, so that if you want to embed them into a low-dimensional subspace, that the subspace has to be a power of n. The dimension of that subspace has to be a power of n. And okay, so with Gilles Pizier and Guidon Shechtman, very recently, just appeared also Schatten one. Okay, so in S1, the Schatten-Phänomen trace class, there's also no dimension reduction, and that's the extent of what we know. And what's going on here, in all of these things, there are two aspects. First of all, is coming up with the example. I'm going to guess what would be a high-dimensional metric space. That somehow, if you know, it's a finite set of points, but if they lie in a low-dimensional space and you know the pairwise distance is up to a huge factor, 100 million, it forces somehow the ambient dimension to be huge. So you have to, first of all, come up with a candidate. And then you have to argue that somehow these finitely many points forces the dimension to be huge. Here, the example was obvious all along. So L1 sits inside Schatten 1 is diagonal operators. Take the same example that was studied here. Brinkman and Charikar proved that it doesn't embed into any subspace of Schatten 1, which consists of diagonal operators in L1. And the challenge was actually to find the proof that it actually doesn't embed into any subspace consisting of any matrices, not only diagonal. Okay, but it's not a new example, it's the same example. Okay, I'm sorry, but that's all that we know. So open, just answer yes or no for any other space. Okay, so LP, P not among 1 to infinity. And I would say even in L1, which is especially important, we rule out the power of n, but we don't know, we do not know any positive result of the form little of n. So give me n points in L1, lower them into dimension n over log 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 n. Just realize them with distortion 100 million. We don't know that. Okay, so P spaces, Schatten P spaces, any classical Banach space, anything, for positive or negative results, we do not know. And this is so usually when people state open problems, they say it's embarrassing that simple questions are not known. This is much more embarrassing than that, because these are questions that actually people really try to answer. Okay, so it's not just questions that would occur to us and we didn't think about. This is something that's received a lot of attention, and we still do not know. Okay, so that's metric dimension reduction. Very quickly about average metric dimension reduction. So spaces that admit average metric dimension reduction. So for that, I'm just asking for less. I'm not asking for much. You have endpoints in the space, find some low dimensional subspace so that you can embed them via Lipschitz mapping, and you just care about the average distance to be okay in the image. That's all, just the average. One number. So of course, what I said before, I mean, Hilbert space and of course Zierleson, I mean, that's a stronger property, but we also know that LP for every p bigger than 2 admits average metric dimension reduction. That's a theorem that I obtained, I think, back in 2014. Okay, so in L4, you can do that if you care about only the averages. We do not know anything about bi-Lipschitz, but you can do it if you care about just preserving the average. And I wrote LP, but this also works for Schattenp. There is some criterion on the Banach space, which you can read in the paper, which implies this, but LP is the case that we should focus on for now. This criterion implies that the space, it forces these spaces, for example, to have type 2. So, I mean, any space of not of type 2, I have no idea what to do. So spaces not admitting so until 2016, it was not known for any space. So we didn't know of any example. And so the theorem is that, this is something that I obtained in 2016, is that L infinity does not. Okay, so again, L infinity is a very, very quick way to say there exists endpoint metric space, and endpoint metric spaces, arbitrarily large endpoint metric spaces, so that if you want to realize them you want to map them into some k-dimensional space, okay? In such a way that the mapping is Lipschitz, and you only care that in the image, the average, one number, is the same as the average distance. That's these finitely many points lying in this continuous k-dimensional space. If you know that the average is right, and the mapping is Lipschitz, this forces the ambient dimension to be huge, and to some universal constant. Okay, so that's it. So we do not know anything else. That's all that's known. So, of course, many open questions, but here's one of my favorites. I believe it's tractable. What about L1? So, I mean, there was P bigger than 2, but just any P less than 2 would be interesting, but does L1 admit average metric dimension reduction? So your first guess would say, okay, it doesn't admit by Lipschitz metric dimension reduction, so let's look at those examples. So all the examples, there were 2 known, there is one more forthcoming in, which is inherently different in a paper of mine with Robert Young. There are 3 known examples of spaces which lie in L1 and require high dimensions in a by Lipschitz way. All of those can be embedded on average if you just care about the average distance into the real line. Okay, in 1 dimension. So the reason these configurations, finite configuration of points in L1 are inherently high dimensional is that when you map them into low dimensions, there will be a pair of points that will be contracted by a lot. But these pair of points are a tiny, tiny fraction. They're little o of all the other of all the points. So showing that in L1 there is no average metric dimension reduction would mean finding a collection of points in L1 in such a way that the reason they're not in low dimensions is much more pronounced. It's going to be everywhere. When you're going to embed them in a Lipschitz way into low dimensions, you're going to see an average necessarily. The distance messed up by a lot. Okay, so this is inherently different from all the examples. They're 1-dimensional in this sense. Okay, so I think it will be interesting to find a counterexample because that would be a really, really interesting bad subset of L1. And a positive result will have, I can imagine 1 already, but probably much more because it will involve understanding, will have algorithmic applications. So there are situations where we care about averages, and embedding into low dimensions means that you can represent the metrics in a compact way using a small number of bipartitions. But just for now, as a motivation for this question is that all the examples that we know indeed are not realizable in low dimensions, but because of a little o fraction, a tiny fraction of the pairs of points, some special pairs of points that are always contracted, but not a typical pair. Okay? And I'm sorry, but that's all that's known. Okay, so the big open question is prove anything. Okay? Outside of this realm. Okay. let me before I explain the proof, I wanted to mention all kinds of applications, but I think I want to jump into the proof. So there's many more applications of this theorem, etc., that I was planning to mention, but I will just skip into the proof because I want to show you what Matuszak did, because it's interesting, and I have a survey on this, and you can see everything in it later. So just one thing I should say, that whenever you prove that L infinity does not have metric dimension reduction, the conclusion is that any space without cotype doesn't have it. Okay, because you can put the bad examples in that space. And there are all kinds of spaces that we know do not have cotype for a non-trivial reason. For example, this free space over L1. This is what Bourgain proved. So the conclusion is that you can concoct a family of n measures on L1 or a sufficient high dimensional RK, that even though these are only n measures, if you only care about pairwise Wasserstein-1 distances between them, you cannot find new measures which are supported in a small number of points. And the pairwise distances, or even an average, are what they should be. So this is something that I was interested in, is still open in low dimensions, but it's related to image compression. Suppose you have a family of measures, n of them. A priori, they could be supported on many points. But I just care about pairwise distances in Wasserstein-1 up to factor 100 million. So my question is, can you find a subset of L1, of the underlying metric space, which has a small number of points, and new measures just supported their sums of the Dirac masses on these few number of points, such that the pairwise distances on these approximating measures with small number of delta masses are like the total number of points. And the answer is because of what Bourgain proved, that there are these really high dimensional measures that cannot be realized using a small number of points. We do not know this over R2. That would be very interesting. There is some indication that over R3 this is very bad as well. And there are all kinds of other things that I'm just going to skip. One final thing before I get into Matuszak's statement and proof. So I want to just discuss the case which is not covered in there, which is distortion when alpha is log n. Okay? So Bourgain proved that any n-point metric space embeds Lipschitz with distortion big O log n into L2. But of course, because once you have this image of these points in L2, you can do a random projection. You can apply Johnson-Lindenstrauss, so you can even say the dimension is log n. Okay, so any endpoints can be realized with Lipschitz distortion log n into some log n dimensional space. And the question that I want to ask is, can you do little O of log n? Okay, so can any n-point metric space be embedded into some k-dimensional normed space with distortion log n space X, and the dimension is little o. So can you just get below log n? Now, the first guess is that it should be yes, the answer to this question. Because the log n in Johnson-Nishaus has a meaning. And that meaning is if you just look at the n simplex, so you have a collection of points, the distance between any two of them is 1. And if you want to realize them with distortion alpha into a k-dimensional space, then the balls of radius 1 over alpha are going to be pairwise disjoint and contained in some big ball. So the balls of, in the way my normalization, the balls of radius a half are going to be pairwise disjoint and containing a big ball around one of them of radius alpha, right? And that forces, just because of volume considerations, the underlying dimension to be at least log the number of points. This is just packing disjoint spheres into a low-dimensional space. But if you allow alpha to be log n, then you have balls of radius a half, where the yi's are disjoint, but the alpha is log n, and they're contained in a ball of radius log n, big O. So what does this force the dimension to be? X. The same volume consideration, you get log n to the power k, k is a dimension, has to be at least n, so that forces k to be, and that's really the natural bound, log n over log n. So the volume consideration, if you allow a radius going to infinity, means that just from volume purposes, the lower dimensional space has to be at least log n over log n. That's clear that I didn't write the computation, it's a simple computation. Is this clear? And moreover, if you track the bounds in the Johnson-Nishaus lemma, that's what it gives. So it is true that any endpoints in Hilbert space, a random projection into a subspace of dimension log n over log n, has distortion log n. So you can realize any endpoints via random projection, the same proof, in little of log n dimensions. So why am I asking this, given that it seems so natural that you could do it, and indeed you can do it for subsets of Hilbert space, is that I know that the volume considerations are not good here. So what we know, this is from a survey that's coming out, is that actually in this setting, the dimension of x must be log n over log n. That's what I just proved, but bizarrely I can get another log. Okay, so this computation was that just from volume reasons, if you want to embed with distortion log and you need this much dimension, I can get another log in the denominator. So that's not a volume reason. Okay? And moreover, that cannot be a Euclidean metric which does this, because I said that JL does reduce you to dimension log n. And I also know that dimension of x is indeed log n if x has non-trivial type. Okay, so I mean the constant here depends on the k-convexity constant. So if you could indeed embed every normed space with the distortion in Bourgain's theorem into some normed space, it will not be a space of non-trivial type. Okay, so you can find endpoint metric spaces that require indeed, even if you allow distortion log n, and there is room in terms of volume, there is actually no embedding into little of log n dimension. So this is a curiosity. I don't know what to believe. It would be really nice if something like this is the answer for a question like that, but I do not know. Okay, so that's a concrete question about distortion log n. And how much time do I have?
10 minutes.
Okay, so it will be. for L infinity, I also know for a different reason that you cannot do this. So it will have to be some sort of space that is adapted to the, well, I don't know. I don't know what is the answer. But not L infinity. Okay, so let me get to a coarse version of Matuszak's theorem. Okay, so now I'm going to discuss this theorem of Matuszak from '96. I'm really doing injustice to the field. I'm not mentioning any application whatsoever, but there is really a lot more to say about all of these things. So let me tell you what the theorem is. So this is, I guess, impossibility. Of course, dimension reduction. And it says the following, so suppose that you're given two moduli, let's say little omega and capital omega, increasing and tending to infinity, and then bounded. Then there exists a number beta, which depends on these moduli. I'll give a formula of what I know how to get. I'm not claiming that this is the right, but it's positive, okay? Such that for every n, there exists an n-point metric space M, which depends on n, and two moduli with some metric, which again depends on these things, such that if X is any normed space, any finite dimensional normed space, such that there exists a mapping f from M to X, which satisfies that f of x minus f of y is between these moduli, for every x and y, and m, then this forces x to be at least n to this beta. And I'll tell you what beta that we get. So the beta that we get is going to be that's what the proof gives. We look at the supremum over s bigger than 0 of s over the lower modulus inverse applied to twice per big modulus. But that's what the proof will give. Okay? So, but in particular, so what Matuszak proved is the case. So by Lipschitz is the case where omega s is alpha s, and little omega of S is S, and then this becomes the dimension of X is at least n to some universal constant over alpha. Okay, and this is sharp. So sharp up to the C, to the value of the constant. This is due to Johnson, Lindstrauss, and Shechtman. In '87. So they were working on this Johnson-Lindstrauss equation, and what they showed is that any n-point metric space embeds with distortion alpha into some k-dimensional norm space where k is n to a constant over alpha. So this is really the worst possible space. But so that's what Matuszak was interested in, and all I'm going to show, well, I don't know how much I'll show, but I mean, this is really amounting to the proof there amounts to just going through his proof and understanding that it can be applied to general moduli. But for example, you can consider snowflakes. So let's say omega of S is square root of S, and capital omega of S is alpha square root of S. So this means you ask what is the smallest k such that any n-point metric space, if you raise the metric to the power a half, it embeds with distortion alpha into some k-dimensional normed space. And when you plug this in there, then you get that the dimension of X is at least n over alpha squared now. This is what, just plug it in there and you'll see it, okay? Because omega inverse is squared, okay? And this is sharp as well. Any power, any snowflake, you will get 1 over alpha to the 1 over the powering of the metric. And there is also a converse to it. So you can always realize into that embedding. So this is quite, even though I don't know what, okay, they're up to constants, I don't know what happens in general moduli, but this is quite good. This gives the answer for many, many coarse moduli, which is actually sharp, the minimal dimension. Okay, is that clear? So we know that there are bad spaces which don't embed coarsely. There are other types of bad spaces which don't embed an average. And well, have a look in the survey, you will see that the answer is different. So the difference between average and coarse is real. There are different asymptotics there. So these are truly different reasons for this phenomenon. The two proofs, one that works for average, one works for coarse, they're not the same proof and they're inherently different. Okay, so I'm out of time, but let me tell you what the examples are and then explain what is the engine that gives the proof. So, So it's really very beautiful, in my opinion. So what Matuszak does, he defines, he doesn't state it this way, but he defines a notion of a random metric space, which can be associated to every bipartite graph. So you start with what's called a template graph, and I can do a distribution over finite metric spaces. And what we're going to show is that with huge probability, these metric spaces are inherently high dimensional. They cannot be realized in any low dimensional space. That's not the way it's phrased in Matuszak's proof. There it's some proof by contradiction. It cannot be that all of them are bad, but it's actually with huge probability, and that's a useful fact to know for other things. But let me explain you what the bad guys are. So start with any graph. Any bipartite graph. G. So there is the left side, the right side, and edges. I need to leave me something. So this is L, this is R. Let's say that the vertices are A1 up to AN, and here it's B1 up to BN, and there are some edges going across. Okay? So L and R are A. whenever you do that, whenever somebody hands you a bipartite graph like that, what I'm going to do is I'm going to duplicate the left side. Matuszak, what he does, he duplicates the left side, so he adds another, call it L prime. Okay? So, and so the total number of points here is now 3n. It was 2n before, now it's 3n. And now for every edge, so if ij was an edge in the initial graph, so let's write a I and bj here, and there was an edge here. Okay? So for every edge independently, I flip a coin. Let's say heads or tails. Okay. If I get heads, I keep that edge. I still draw it in this graph. Okay. But if I get tails, I delete this edge from the graph and draw the same edge, but from the clone of AI, from AI prime to bj. Okay, so for every edge, I flip an independent coin. If it's heads, then there is no edge at all between AI and bj, AI prime and bj, between the clone of AI, the new copy. If it's tails, then I delete this edge, and the edge is actually going from here. Is the distribution over random graphs clear? And then you take the shortest path metric on this. And the theorem is going to be with that. So the precise statement is that suppose the initial graph that G had the shortest cycle in G has length G, and G satisfies some conditions, strictly bigger. Then you consider the metric space. So the new graphs here are, if the coin tosses, they're plus minus one coin tosses from every edge to this, so the new graph I'll call G sub epsilon. It's a random graph, and there are 2 to the number of edges of them. So then the metric G sub epsilon with the shortest path metric, but I truncate it. So minimum of S times the shortest path metric, X, Y, and T. So there's a truncation parameter and there's a rescaling parameter. That's the random metric space that I would consider. This metric space satisfies the conclusion. Or maybe. Then this metric space, so if this embeds with moduli omega and omega into a k-dimensional norm space, then k must be at least some universal constant of over the number of edges over n. So then, I guess this, with probability, the probability that this does not happen is exponentially small in the number of edges. Okay, when you choose the coin flips uniformly, it's random. Is that clear? Then, with probability, except for an event with probability smaller than whose measure is less than e to the minus the number of edges, you have this. Okay, and then the way you finish is you choose a graph, a random construction, whose girth is, you take the S where this beta is the supremum. This is the S that you choose. You look at this random metric, but you choose a graph where the number of edges is the biggest possible, which is easy to get. It's n to the 1 plus a universal constant over g. That's a random graph. You take a random graph and delete all short cycles, okay? And if you plug this in, then you will get the statement of the theorem. And I'm really over time, so now I'll really wave hands. So what did Matuszak do, and what do I do here? And I can explain to anybody after. So you suppose, you look at the family you look at the subset of the graphs which do happen to embed into some n-dimensional normed space. And for each one of them, you fix an embedding into into some k-dimensional normed space where k is small. So you fix an embedding of this graph into the k-dimensional normed space. So now the image, call them f. But the f depends on the coin tosses. And you make two observations. One of them is that these graphs, I changed the geometry in this randomness. But one thing is clear is that I did not introduce any cycles. Okay. So so what is the distance in the initial graph between AI and AI prime? So let's look at the shortest path from AI to AI prime. Okay, it goes sometimes between the top part, the new clone vertices, etc. But I can collapse it back, and that will induce a path starting from AI and going back. And in this construction, I never duplicate an edge. So that means that if there were a path between AI and AI prime, that would mean there was a cycle between AI and back in the initial graph. So this means that in this random graph, what I do know is the distance between AI and AI prime is always at least the length of the shortest cycle. But I know that depending on the coin flip, either AI is close to BJ if there's an edge, or AI prime is close to BJ, but only one of them because their initial distance is big. And okay, so that's what I'm gonna use. How I'm gonna use that, I'm gonna take the normalizing functional that normalizes the distance between AI and AI prime in the image, f of AI and f of AI prime. There is so you look at the normalized functional, and the normalizing functional, it's a unit functional which in the image has big distance, at least maps the difference between this functional applied to f of AI and f of I prime, at least omega of g, what's written up there, right? And using this functional, I build a matrix, an n by n matrix, which that's the trick of Matuszak found of applying the functional to certain points, and you get a certain matrix, which is a closed formula. And the fact that the target space was low dimensional means that this matrix is low rank. But this is designed in such a way that along the entries, which correspond to edges, the sign of what's written there, so you look, the entries is indexed by I and j, all I and all j. But some of the entries ij correspond to an edge in the graph. When you have an edge in the graph using these observations and playing with a triangle inequality, you see that the sign of what's written there in that entry is exactly the coin flip. So that's why we designed the parameters in such a way. So in the entry, let's say, suppose there was an edge between vertex 7 and vertex 100, and the coin flip was +1, heads, then it's going to be some number written there, but it's going to be positive. And if the coin flip was -1, then the number that's written there is going to be negative. So I have these matrices which are, in some locations, I know the sign patterns. Okay, but what does it mean that a matrix is low dimensional, is low rank? So when I'm saying that a matrix is low rank, means that you can write it, if this were n by n, you can write it as an n by the rank times an r by n matrix. So it's actually a product of two matrices with small number of entries. But that means that the entries of A satisfies a family of quadratic polynomials. Think of the B and C as variables of this equation. and they satisfy a certain family of quadratic equations. So they lie in some low-dimensional variety, which is determined by two-dimensional by polynomials of low degree, which I can write down. And there is and in the 60s, Milnor and Tom show that if you look at a low-dimensional variety that is determined by small number, by polynomials with small number of variables, this is the rank, and low degree, then they cannot attain many sign patterns. I mean, it's worse than, I mean, the sum of the Betty numbers are small, but we're just looking at the connected components of the variety. And when you crunch the numbers, it becomes the bound. So it's an encoding scheme which, from low-dimensional embeddings, produces a family of low-degree polynomials such that the variety they carve out has too many connected components. And that's the punchline, but it gives very sharp results, as I said, even for snowflakes, etc., when you actually crunch all these numbers. And I was extremely ambitious. I thought I would show you all the proof, but there we are. I'm still here, and I'm happy to show the proof to anybody in the break. Okay, thanks.
It works. So, question, please. Guillaume?
Okay, you need to hold this.
Maybe you should say something about applications, maybe for nearest neighbor.
Okay, so something is really, this is a very big area, and there's a huge amount of literature. And thanks for the question. Yeah, thank you. Those who can see, that was Guillaume. It was not planted, but thank you. Okay, I actually probably erased it already. There was a theorem that I stated, a recent theorem that I proved about the impossibility of average dimension reduction. Okay, so which was that there are bad metric spaces which do not embed even an average into any low-dimensional norm space. Now, this theorem, so it sounds like a negative result, right? It's bad news that there are these metric spaces which are very high dimensional. Just like here, we can look at these bad guys, and they're bad. Now, the advantage of that theorem is that, unlike this random construction, it gives a criterion for which metric spaces are inherently high dimensional. And the criterion, so the theorem is that any expander, if you have a bounded degree graph, for example, there are other, with a spectral gap, then that doesn't embed an average into any low dimensional metric space, Banach space. So there's a way to look at a metric space and decide whether it's high dimensional or not. Okay? I can look at a graph and I can and compute its second eigenvalue and say, oh, if the second eigenvalue was far away from the first eigenvalue, then it's not realizable in the low-dimensional norm space. But of course, there are many graphs which are realizable in low-dimensional spaces. You can just force it to happen. Look, take your favorite k-dimensional space, take an epsilon in the unit ball, and say that these are the vertices, and say that two vertices are joined by an edge if, let's say, their distance is at most 100 epsilon. I'm inventing parameters here. So if epsilon is small enough, this guy, the shortest path metric on this graph, will be embedded an average in the norm by design, because I designed it as an approximation of the initial geometry. And there are many geometric constructions which do produce metric spaces which are shortest path metrics and graphs which are inside low-dimensional space. So now let's flip this bad news on its head. So instead of saying there is a bad metric space which doesn't embed into low-dimensional, into any low-dimensional norm, say we have actually a criterion which says that if a graph is already in a low-dimensional norm, it cannot have a spectral gap. So that's actually a structural fact about graphs which are drawn inside low-dimensional norm. Because spectral gap means that you can partition them into two pieces with a very small boundary. Okay? That's if this graph was embedded an average in the low-dimensional norm. If it wasn't embedded an average in the low-dimensional norm, then that means that there must be a ball which contains a huge proportion, a small ball of small radius that contains a huge proportion of the points. That's what non-average embedding means. That's one of the advantages of looking at average versus by Lipschitz. And now this partition is also a meaningful partition, the ball and its complement, because there's a cluster. And there's this criterion that if I draw a graph in a norm, either the shortest path metric is a good approximation of the distance in the norm, just an average. Therefore, by spectral theory, I can partition it into two pieces. Or this graph is actually clustered in the norm. There's just a ball of small radius that's from non-embedding an average, which contains a big proportion of the points. So I can partition it into the ball and its complement. So anybody who ever did hierarchical partitions or Calderon-Zygmunt decompositions wants to jump all over this. So we can use this fact to do partitions of high-dimensional norms, which in each step you either take a look at the spectrum or take a ball and its complement. And the spectrum is somehow the intrinsic geometry tells you how to partition. It could be a very, very complicated bipartition. You just know it's level sets of the second eigenfunction of this embedded graph. And when you apply this iteratively, you get some tree structure of an arbitrary low-dimensional norm, which has parameters that we never knew before. And in particular, it solves it's one general theorem about availability of algorithms for nearest neighbor search. So you have a collection of points in a norm, and you want to find, a new point comes along, and you want to find which one is approximately the nearest one to it. So it gives a family of algorithms which just work with the quantifier every norm. It doesn't matter which norm you take on an RK. We get this algorithm, and even in specific norms, like Schatten-1, or operator norm, Schatten infinity, this gives algorithms that people looked at in these specific norms and didn't know how to do for many, many years. But overall, it just gives a new structural fact of low-dimensional norms, which the partitioning step is not the usual thing that we do, like partitioning into cubes and subcubes, but sometimes you just say, okay, this graph can't have a spectral gap. Look at the second eigenfunction, look at its level sets. One of them will be the bipartition, and you iterate and you get a structural representation of low-dimensional norms, which is useful, and it's somehow dictated by the intrinsic geometry of the norm and not by something that we impose, like a grid. Okay, so this is all very new, but these are the kinds of applications of so this negative news can be flipped on its head and can be viewed as positive news. That it's actually a criterion for high dimensionality, which means that any low dimensional object does not satisfy the criterion, and therefore it has some decomposition. Okay, so there's going to be several papers coming out on this, which apply this kind of philosophy.
Any other question? Yes, we can.
So my question is on the upper left blackboard, which is still there, on L1 and S1. So
yes.
You said that there is a finite subset of L1 that cannot be put efficiently in a small dimensional subspace of even S1. Mm-hmm. Can you put it efficiently in a small dimensional subspace of L infinity, or is it?
Excellent question. So in all of the, I formulated this property of admitting average dimension reduction as a property of one space.
Yes.
But it's actually a property of two spaces.
Exactly. Yeah.
Okay. So you can have, or maybe two families of spaces if you want. You have an endpoint subset of one, and you want to realize it in a low-dimensional subspace in the other family. In this formulation, it's even more wide open because we don't, even for one space we don't know the answer. And for L1, what you asked is a big open problem. So it could conceivably be true that every endpoint subspace of L1 embeds with a constant distortion into some norm space of dimension even log n. None of the examples rule this out. And there are some strategies. I can suggest two different strategies to prove it. There is a paper coming out of Andoni Neyman and myself where we showed that a very clean question about Lipschitz extension, which I really put a lot of effort into disproving, but I don't have that's my only evidence why it might be true. But it's something about extending Lipschitz functions from nets. If it were true, then it would imply this theorem. And I have some other conjectures which I know that would imply this. So I think there's a good chance, I would say probably a very good chance that an endpoint subspace of L1 is not an endpoint subset of L1. Doesn't have to lie in a low-dimensional subspace of L1 itself, but you can cook up a clever norm, which is low-dimensional, so and it's realizable there. But I think that would be a very nice result. We have no idea how to do it.
Any other question? Okay, so I think we should thank our speaker again. Thank you, Assaf.